Oh. Right, we'll give it another minute for people to join. Right, okay, let's crack on. There's 25 of us now. Good afternoon, everybody, or good evening, or good morning, wherever you are tuning in. So today is the second webinar of the 5 webinar series. Let me introduce the panelists for today. So we've got Steve Tate as the ICOR president, and we've got Yunan Gao as the ICOR vice president. And also on the panelist is Bo-Wei Zhang. He is the focal point of CSCP, who has helped organize all of this. And lastly, we've got Professor Yong Xiang, who is our presenter for today. And Steve, do you want to go first for your introduction?
Yes, of course. First of all, I'd like to pay thanks to the chair of the ICOR Aberdeen branch, Mei Ling. So thank you very much for hosting this webinar for us. This is the second of our joint webinars to be held with CSCP, and you're all very welcome, and hope you enjoy the proceedings that follow. I'm going to give you a short introduction to the work of the Institute of Corrosion in the UK, otherwise known as ICOR. I'm the current president, Stephen Tate. I just wanted to give you a little background as to how this joint event came about. My colleague, Dr. Yunan Gao, has been in contact with CSCP, which is the Chinese Society for Corrosion Protection, over the last 12 months, and we've held a regular series of meetings with CSCP, and this has culminated with us visiting China in October and attending the International Corrosion Congress in Xiang. And also at that point, we came to an agreement with CSCP and jointly signed an MOU between us for future cooperation. So we're hoping that this will be the start of something much larger, where we collaborate in the award of awards to students and providing joint conferences and training between us. So it'll be a good working relationship going forward. So the images there, the pictures there, just show the signing of the last most recent agreement in Xi'an. Next one, please. So briefly, the ICOR was founded 65 years ago in London as the British Association of Corrosion Engineers, BACE, and has now become the Institute of Corrosion more recently, or known as ICOR. We are based in Northampton near London with 8 UK regional branches from Aberdeen, Central Scotland, Newcastle, Manchester, Sheffield, Birmingham, London, and Wales. So those are our key UK branches. Our principal aim is to advance the understanding of science, technology, and engineering practice related to corrosion control, and to facilitate the exchange of information and ideas for public benefit. Thank you. Next slide. So this just quickly shows the distribution of our branches around the UK. As you're probably aware, the UK has a population of about 70 million. So this is how we're currently spread out around the UK, but we're very much looking to expand our activities overseas, both in China and elsewhere overseas. So we are very much expanding our profile presently. Thank you. Myself, as the current president and twice past chair of the ICOR Aberdeen branch in Scotland, similarly for our current vice president, we've also served a similar amount of time for the Aberdeen branch previously, prior to be taking up our positions on a national basis. So between us, we have about 60 years of experience, and supporting us, we have a group of 4 trustees and council members of 20 currently. Thank you. So our current membership is about 1,500 members, and we're targeting a 10% growth by 2026. About 20% of those are student members, about 35% company members, and the balance is very much individual members supporting our local committees around the UK. Thank you. We publish regularly a corrosion management journal, which incorporates normally 3 or 4 technical articles every issue, and we invite our members or prospective members to contribute articles for publication, future technical publication. Thank you. You'll see from our website there are various grades of membership. If you're interested in joining or working with us in any way, please look at our icor.org website, www.icor.org website, to get further information about membership. Thank you. Just briefly, our main divisions, we have a corrosion science division, which obviously focuses more on the research side of things and close collaboration with universities. We have regular symposiums and student awards for those involved in CSD. Next one, please. Next slide. And also have our, if you like, the more industrial side of our activities, which is our Corrosion and Engineering Division, CED. We have regular events, usually based at one of our facilities, laboratory facilities around UK. This one picture was taken at the National Physical Laboratory in London, where we held our 2023 event. But it is a good forum for exchange of ideas and for formulating new standards and working documents for the industry. Next one, please. And we have our 3rd major division, which is our Young ICOR division for corrosion members under 35 years of age, where we help them develop within the industry, provide a network of contacts for them to integrate better with organizations and progress their careers to chartered status. Thank you. And we've recently started supporting University of Manchester with scholarships. So we provide funding for 6 students every year to help them with their studies at Manchester University in corrosion. Thank you. And we have both registrations for chartered scientist and chartered engineer, which can be applied for through ICOR. Once you have ICOR membership, we can assist you to get either a chartered scientist or chartered engineer additional professional qualification. Thank you. That's all for me just now, and thank you very much, and look forward to our speaker joining us shortly. Thank you.
Alrighty, thank you, Steve. So up next is Boy. He's gonna give you a quick introduction on CSCP.
Yeah, sure. I think you should stop the sharing of, yeah. I will give a short, brief introduction about CSCP. Hello, everyone. I'm Bo Zhang from University of Science and Technology, Beijing, and also Chinese Society for Corrosion and Protection. And what we are is Chinese Society for Corrosion and Protection. Is a member of China Association for Science and Technology, and CSCP was founded in 1979. Now consists of over 8,000 individual members and 287 group members. We have 7 working committees and 25 specialized committees. And we also have some branches located in at Beijing, Shanghai, and 15 other provinces and cities. And our president is Professor Xiang Li, and the Secretary General is Professor Chen Jiexin. And also we have 10 vice presidents from different institutes of China working on corrosion and protection. And what we do is mainly focusing on the 5 aspects. And the first is the academic communications, like the conferences. And also we do some science popularizations. We have a journal, it's called a Corrosion Protection Fund. It's like an interview of the senior and scientists working on corrosion protection. And also we provide industry service, like the training and education and consulting to the industry. For example, the steel makers and the shipyards. And also we can issue some technical or testing standards, and also the academic awards. And the last part is our international relations. For the international collaborations, CSCP now is a member of International Corrosion Council and a World Corrosion Organization. And we are also the co-founder of Asian Pacific Material and Corrosion Protection Association. And we have built bilateral cooperation with organizations from 18 countries around the world, like the US, UK, France, Singapore, and so on. So since we in China, we have very huge market for corrosion protection. So we have some technical or trainings and a certification program. One part is from NACE, as we all know, the CP series, and also we have our own trainings and a certification program. And during the past consecutive 3 years, we have held 3 international conferences on corrosion protection. And I think for each year, there were speakers from UK, like in the 2022, the International Congress on Materials Degradation and Protection is a online webinar. We invite Professor Andrew Berg. I think he's also here as an audience. And also for the last year, we held the 19th Asian Pacific Corrosion Control Conference, and Professor Andrew Berg from University of Manchester and Gareth, they both joined us for this conference. And for this year, just last month, we held the 22nd International Corrosion Congress in Xiang, China. And for this Congress, Stefan and Yunnan and Xiaorongzhou from University of Manchester also joined us for this Congress. I think it was a great success. And that's all for my introduction about CSCP, and you can refer to our official website or the WeChat account for more information. Okay, thank you.
All right, thank you, Boe. So before we begin our presentation, I'd like to note that this session is being recorded, and if you have any questions, please enter them in the Q&A box, and they will be addressed at the end of the presentation. And for our presenter for today, it's Professor Yong Xiang. Yong Xiang is a professor and a doctoral supervisor at the College of Mechanical and Transportation Engineering, China University of Petroleum Beijing. He's also the director of the Laboratory for Low Carbon Energy Equipment and Material Protection, and serves as the deputy dean of the Ocean Engineering Institute. He earned both his bachelor's and doctoral degree from Tsinghua University and was a postdoctoral researcher at Ohio University. He's an active member of multiple committees under the CSCP, including the Corrosion Inhibitor and Water Treatment, Oil and Gas Field, and Pipeline Corrosion and Safety, and Non-Metallic Corrosion Resistant Materials Committee. Dr. Xiang has led 2 projects funded by the National Natural Science Foundation of China and 2 projects supported by the Beijing Natural Science Foundation, and has published over 30 academic papers with more than 500 citations. His achievements have been recognized with several awards, including the 2nd prize for scientific and technological progress in Shanxi province, the 1st prize for innovation from the China Association of Invention, and the 1st prize in scientific technological achievement from the China Society for Corrosion Protection, and the 2nd prize for collaborative innovation in industry academia research initiative. And his main research area include carbon capture, utilization, and storage, CCUS, and corrosion protection. So please join me in welcoming Professor Yong Xiang.
Okay. Good evening. Good morning. I also have to say good noon to the people that you are listening to my presentation. My name is Yong Xiang from China University of Petroleum. And today I would like to thank Dr. Bowie Zhang to invite me to give such a presentation, because for me, maybe I gave the English presentation is in USA in 2014, 10 years ago in San Antonio, in the NACE. So for me, it's a long time. I'm not going abroad to taking part in the conference. So for today, I think it's a very good opportunity for me to tell everybody my work for about 17 years on the CCUS corrosion. So today I just want to talk some of the phenomena, especially the spontaneous corrosion inhibition phenomena in the CCUS system that we found in our research. And we also want to discuss about their mechanisms. Maybe some of the mechanisms is not very clear, but I would like to discuss it with everybody. So here is my report outlines. I would like to introduce my research group first, then I will give you a research background. I would like to talk to you what is the CCUS and what is the challenge, the big challenge of the CCUS we faced. What is the CCUS? I have to talk first. CCUS is a carbon capture and utilization and storage. So for the 3rd part, I would like to introduce some of our research results and give you a discussion on it. So we also would like to give the conclusions and the prospect at the 4th part. So I'm sorry, because today I have get a cold. I have some problem with my voice. So maybe my voice is not very clear, but I will try my best to give this presentation. So first of all, I would like to introduce our laboratory. Our laboratory name is Laboratory for Low Carbon Energy Equipment and Materials Protection, which is dedicated to the equipment of low carbon energy protection and failure in the field of this area. So we are usually focused on the CCUS, focused on the enhanced oil recovery and hydrogen utilization. So you can see some of the corrosion happens under the downhole. So we have 3 professors in our group. We also have 3 associate professors and 1 lecturers. We have different background. My background actually is thermal engineering, but I doing corrosion when I get my PhD degree in Tsinghua University. Dr. Yan Wei, he's working on the wearable integrity, and Professor Wang Jiangyun is working on the multi-phase and erosion corrosion. So they have different background. We cooperate together so we can do better work, I think. For me, I think the organizer have introduced my resume. I graduated from Tsinghua University. I get my PhD degree in 2012. I get the postdoc in Ohio University. In Tsinghua, I doing some research related to the supercritical CO2 corrosion. That means when the CO2 in the supercritical state, transportation, there will have some of the corrosion problems inside. So internal corrosion of the CO2 pipeline, I'm doing research with this, especially when it contains some of the sulfur dioxide and oxygen, oxygen impurities. Then when I go to the Ohio University, I'm doing some of the work related to the MDA corrosion, that is the CO2 capture, especially for the chemical absorption technology for the CO2 capture. I'm doing something related to the MEA corrosion, MDA corrosion. When I come back to China University of Petroleum, Beijing, 10 years ago, I'm doing some of the research related to the downhole tubing corrosion, especially now I'm working on the storage system. They will have the corrosion problems. So that's my research. We also have a lot of good experimental equipment. We also developed a SuperCorp software, which is used by Changqing, Daqing, Jilin, Zhongyuan, and Yanchang oil field all over the China. And we have get a lot of the awards and published a lot of the papers. That's what we already have, including the Shanxi Provincial Scientific and Technology Progress Award and the CSCP First Prize Award. That's our paper. So we have more than 30 essay papers related to the CCUS corrosion. You can check my personal website to see these papers. So the second part, I would like to give you the research background, what I do for the 17 years. What I do is corrosion in which environment, that is in the CCUS environment. What is CCUS? I have told you, because of the climate change problems, we have to reduce the carbon dioxide emission to the air. So we have to capture the CO2, then transport it to the utilization and storage sites. We use it to enhance the oil recovery or doing other things for utilization. And then we will storage onshore or offshore. We also have a dual carbon goal for China. That is the carbon peaking and the capping carbon neutrality goals. So CCUS is very important for these two goals to realize. But we also still have two big challenges for the CCUS nowadays. One is the high energy consumption for capture. As we all know, we have to use energy to capture the CO2, but it will use a lot of the energy to capture the CO2. So how can we reduce the CO2 capture energy consumption is a very big question to answer. But today we would like to talk about another challenge, that is the uncertainty of the storage safety. Because as we know, after the CO2 injected to the underground, the corrosion is still happening on the downhill area, not only on the cap rock, but also on the downhole area. If the corrosion slowly happens maybe 100 years, 1,000 years, 10,000 years, maybe the CO2 will come out. They come out together at a very large amount? I'm not very sure. So my work is to try to answer these questions. So here is some of the CCUS corrosion characteristics that I summarized, including the wide range of the equipment and materials. This is because this is very important, because it may have the power plant captures facilities, transportation pipelines, and injection and storage tubings. So there is a lot of materials. And the media inside this system is also very corrosive. As we all know, CO2 is very corrosive. If they have the impurities, including H2S, NOx, SOx, oxygen, it will be very corrosive. And in this systems, it will be a multi-phase environment. We have a four-phase for things like CO2. It can be gas, liquids, solid, but it can also be the supercritical CO2 phase. So in different phases, it maybe have different corrosion mechanisms. Another thing I have mentioned, that is the impurity. And another thing is that when the impurity come inside the system, the mechanisms can be different. And also the product films composition is complex and variable with the time. Maybe for 1 year corrosion, it is this. After 10 years, 100 years, maybe the corrosion products will change. I let my PhD students doing this researches. And also we lack some of the corrosion protection experience. So I think we have to do a lot of work on these areas. So for the impurities, if you use the different capture technologies, you will get different impurity concentrations, like the oxy-fuel combustion capture. You will get a lot of the oxygen inside. If you use the pre-combustion capture technology, you will get a lot of the H2S inside. So you use different technologies, you get different impurities, then you get different corrosion mechanisms, different corrosion laws. So that's the different things we meet it. So here is a different CO2 capture comparison. We have listed the advantages, disadvantages, and the capture cost. As we all know, chemical absorption is a very useful technology in the gas purification technologies. But when it used into the power plant CO2 capture, it may have some of the new problems, like the oxygen degradations and some other capture technologies. In my opinion, for nowadays, this kind of CO2 capture technology is not very mature. So it needs some of the time to reduce the energy consumption, to reduce the cost, reduce the cost of the technologies. So for the chemical absorption, this is the organic arming CO2 capture systems. Here we have a absorber regenerator. Regenerator is high temperature, maybe more than 120 centigrade. So when it is used to the coal-fired power plant CO2 capture, it may have oxidative degradations because there's a lot of the oxygen in the flue gas. When the flue gas go into the absorber, the oxygen will react directly with the organic amines. So the organic will going to degrade it. So here we have a conference to showing the cost of this kind of capture technologies. You can see there we have to use the electricity to pretreatment, to absorption and compression and liquefaction. So it will cost about more than 100 RMB, and circulating cooling water, every step you have to use it. It also have a cost, maybe 50 RMB. And the most important thing that you have to use the steam, very high pressure, high temperature steam to regenerate the CO2 from the rich arming. When you heat it, the rich arming CO2 inside it will come out. Then the CO2 is separated from other of the gases. So CO2 is captured. So we have another thing is about the definition of the carbon source concentration. Actually, for the coal-fired power plant, it is low concentration carbon source. It is below 20%. Maybe it's 10 to 12% of the volume concentration. So sometimes you cannot use some of the other capture technologies that is used in the chemical engineering to capture the CO2. So the flue gas in China is also a very big amount, because you know that more than half of the electricity in China, we use the coal-fired plant to generate the electricity. So flue gas amount in China is a very big amount. So in these systems, we have a lot of the corrosion problems, like the here we have a reference to see these problems. They have uniform corrosion, they have pitting, but they also have another very big issue, that is the stress corrosion cracking, also can be called ASCC. Here we have a picture that is taken from some of the CO2 capture power plant. You can see here we see some of the cracking. That might be the ASCC, but we are not sure. We are doing some research work to make sure why this crack happens. And also you can see the middle pictures. We have some of the pitting on side of the stainless steel 304. It's caustic stainless steel. It can be also observed, the pitting happens on the surface. Why this happens? We search the reasons. Maybe the chloride ions in the systems accumulated with the time. So when the chloride ion concentration is very high, then maybe the pitting happens. So maybe some of the stainless steel in the fresh new CO2 capture plant, they have no pitting problems. But with the time, maybe several years later, they will have pitting problems because of the chloride ion accumulation. So to the next part, that is the transportation systems. Also in USA, they have a lot of the CO2 pipelines, maybe more than, I think, more than 6,000 or 7,000 thousand kilometers. There is a statistic numbers that is from this year to this year, more than 20 years. They have only 29 reported accidents. Actually, the number is not very much, but you can see for the CO2 pipeline, the corrosion causative factor for the CO2 pipeline for the corrosion is about 45%. So corrosion is a big challenge for the CO2 pipelines. We have to address these problems. So as we all know, there is a lot of the impurities inside of the CO2. If it come into the CO2 pipeline, it maybe have some of the impact on the physical properties of the CO2 mixtures. And in the end, they will have effect on the corrosion and hydrate formations. The corrosion problems also have a lot of the influence factors, including the medium and the materials, environment, and others. For the medium, it depends on the CO2, what CO2 have inside. That is the impurity gases. What is the kinds and concentrations of the impurity gases, especially for the water content. Maybe 12 years ago, we also found the same law as this pictures shows you. This means water content is increasing above the critical relative humidity, then the corrosion rate will increase sharply with the water content. So you have to control the water content in the CO2 pipelines, such as other impurities. Oxygen enhance the corrosion. SO2, NOx will enhance the corrosion. We'll talk about it later. So what is the conclusion for the corrosion protection for the CO2 transportation pipeline? Or suggesting is that dehydration, you have to remove most of the waters inside, then you can control the corrosion very effectively. Maybe below 500 ppmv, maybe 200 ppmv. Maybe in USA they have also a standard for that, maybe 40 ppmv, like that. But if you have a lot of the money, you can use stainless steel, like that happens in Norway. They use stainless steel for the CO2 pipeline. It can also control the corrosion. But when we use the CO2 to enhance the oil recovery, maybe it have corrosion problems for the injection wells. It also have the corrosion problems for the production wells. And at the end, the CO2 will going down to the basin, to the underground. There is a very big challenge that may happen. Will the CO2 come out? When will the CO2 come out? If they come out, what is the dangerous? The dangerous for the people, human being, I think it is dangerous because in more than 38 years ago, in Lake Niels in Cameroon, the natural CO2 come out from the lake, then spread out. There is around 1,700 people died at that moment. So here's another news. That is the world's first CO2 leakage of the CCS or CCUS project that happens in USA, in Illinois. About 8,000 tons of the liquid CO2 and other fluids has flew out to the uncontrolled area. Actually, the news didn't see that the CO2 come out to the atmosphere, but maybe they come to other of the uncontrolled areas. They also have two leakings, which happens in March and July in this year. Why this happens? Because of the monitoring well is corroded, so the CO2 coming out to the uncontrolled areas. So what I want to say, that is the CO2 leakage is a big challenge for the CCUS safety. So we have a lot of the corrosion problems. I have said that the injection well and the production well, they also both have the corrosion problems. And they also have the scaling problems. You can see this picture, there's some of the scaling problems. And after the storage, maybe they will come out in this area. Maybe corrosion happens on the cement, rock, tubing. So do we have any method to control these problems? Actually, for the injection, for the production, we have corrosion control measures. But for the storage, now I think we have so few technologies can be used to control the area, the corrosion in the area of the tubing. So there is another question is how many years we have to storage the CO2 underground? 1,000 years, 10,000 years, or more than that? Actually, we are not sure. So after a long corrosion, maybe 1,000 years, maybe the CO2 will come out from the first phase, second phase, maybe from the tubing, the metals, because of the corrosion, because of the cement, may also have the corrosion problems. We also did some of the work related to the cement corrosion in these areas. So that's a very big question. I'm still working on it. So for the third part, I would like to give you some of the results and discuss about of the spontaneous corrosion inhibition phenomena in briefly. So what our work used is a glass cell, and also we use a high temperature and high pressure autoclave to do the corrosion environment. And also we researched the welded joint electrode. So here we have the welded metal for this area, and heat affected zone area is this area. For the base metal, this is this area. So we have some of the results to show you. This work, I did it 10 years ago in Ohio University. This shows that when the flow and oxygen is both present, in this capture system, you can see the corrosion rate is a line is not going to drop. But when there is no oxygen, you can see the corrosion rate will decrease with time. So what happens in this system, because we think that the flow may increase the mass transfer process and accelerated the corrosion, maybe affected the formation of the corrosion products. And maybe 5 years ago, we did another work. We found it a very interesting phenomena. That is, when you use a fresh new solution, MEA solution, you put the coupon inside it, you will find there is a high corrosion level like this. But if you firstly use the oxygen and CO2 to give a oxidative degradation to the MEA solution, then you will find when the coupon put inside for 120 hours, but also for the degradation is for 120 hours. After that, you put the coupon inside, you will find that for the same time, the corrosion rate for the dirty solution, that is a degraded MEA solution, the corrosion rate is very small. You can see this, small than 0.01, but here we have a very high corrosion rate. We also did SEM pictures. You can see this one. This is the dirty solution for 120 hours emerging. So we can see that there is a very high corrosion rate for the fresh solution than the dirty solutions. So we would like to find the reasons. We also did some of the EIS tests. We also find the same things. We this result is also consistent with the weight loss corrosion result. You can see this line is for the dirty solution EIS spectrum, and others, they are not dirty solutions. You can see there is a very big variable impedance. So we can see in this systems for the dirty solution, the corrosion rate was very lower. And we also did some of the film characters checking, and we found some of the products like the ferric oxyhydroxide, and also for top of seams, we found some of the degradation product on side of the surfaces. That is the hydroxyisomimidazole, that is HEI. That is a kind of the MEA degradation products. So we think maybe the HEI adsorption on the surface of the coupon, then it will reduce the corrosion rate of the A106 steel. That's the reason, because of the degradation product may co-work with MEA, so it reduced the corrosion rate. We also did another AEA has the same phenomena for these things. We also say that this is the fresh solution. This is the dirty solution. The corrosion rate is also much slower, much smaller than the fresh solution. And these things also happens found by other researchers. Maybe I think half years ago, some of the people in USTB, in Dr. Bowie Zhang's university, he come to ask me, he asked me that, Professor Xiang, I found the same things that happens in your articles. Is that correct? I think I answered him correct, because I repeated, and for this AEA, for MEA, and for his work, we also find the same phenomena. So that is the capture system. For the CO2 transport and injection systems, we also would like to check the SO2's effect on the corrosion. Actually, maybe 10 years ago, we think that when this SO2 injected into the CO2 system as an impurity, maybe it will enhance the corrosion rate. But for our test, especially to the atmospheric CO2 system, maybe the CO2 will reduce the corrosion rate, because we found some of the corrosion product formed on the steel surface when the SO2 injected into the system, especially for the initial stage of the corrosion. So we also do the same work for the welded joint steels. we also find the same things. That is the base metal, when the SO2 go into the system, the base metal also reduced its corrosion rate after about 72 hours of the exposure. So we have repeated this experiment. We found the same law, that the base metal has the very low corrosion rate than other part like HAZ, WM. So we also do the EIS test, found the same things. You can see some of the things absorption on the surface. And you can see for the base metal for 22 hours with SO2, there will have a very big of the inductive arcs, not inductive, just for capacitive arcs diameters. That shows the corrosion rate for the base metal is very low. And we also did some of the XPS tests. We found that some of the FES, ferric sulfide, formed on the surface. Maybe this kind of things reduced the corrosion rate of the base metal. So here is the transformation mechanisms which have been found many, many years ago. When SO2 in the no oxygen systems, it will transform from this state to this state, maybe to this state, when it forms the FES, so corrosion rate is going down. Also, we have the another pictures to show the mechanisms. But we don't know, one thing is that why the FES would like to absorb on the surface of the base metal and form the FES product film in this area. Why not in this area? It just would like to form in this area. Maybe we have to find the answers. So for the spontaneous corrosion inhibition filameners, we also have intentional corrosion inhibition measures. I will briefly talk about it. It's about the coating. For the coatings, is also use the metal alloy coatings, but it also have the crackings under the CO2 UR downhole conditions. After maybe 20 days corrosion test, it's cracking like this. So maybe we have to working on it to improve this things. So for the corrosion rate, actually the nickel tungsten coating actually have a very low corrosion rates, except of the cracking disadvantages. For the coating with the organic polymer-based coatings, maybe they have blistering problems in the supercritical CO2 environment. Maybe it's not very proper for this environment for using. So here we have some of the corrosion inhibitors for the CO2 capture systems. It is listed here. It is from very good articles you can cite, you can read. So some of the inhibitors like the imidazoline, quaternary ammonium salt, it can be used in the CO2 system, but the problem is when the impurity comes, what is the impact of the impurity on the corrosion inhibitor? That is unknown. From now on, I think we have to working on it. So here is some of the brief conclusions. Maybe some of the degradation products reduce the corrosion rate. The FES formed in the SO2 solutions is reduce the corrosion at the initial stage. And we also have to working on some of the protection measures, especially for the storage systems. That is a very important issues to make sure that CCUS technology is very safe for the human being, for the world. Okay, that's my presentation. Thank you very much. Thanks.
All right. Thank you, Professor Yong Xiang. Let's go to the Q&A session for now. We've got a question from our Steve Tate. His question is Professor Yong Xiang working towards a lower cost standardized solution for coal fuel emission?
Yes, thanks for your question. I would like to answer your question use these pictures because lower cost, lower energy consumption is very important for the CCUS technologies. In my group, actually, I'm working especially on the corrosion problems that is more related to the safety of the CCUS. But in your group, Professor Fan Yanfang is working on the CO2 capture technologies, especially for this kind of technology. I listed here, it's about absorption separation. Maybe our work in this area, we're working on this lower cost solution for the China coal-fired emission. So this is a very big task because I here have data show you that when we have a lot of the CCUS project in in the world, I don't know, but in China we can estimate. Here we have a prediction by some of the research. More than 85% of the China fossil power plant will have to use the CCUS technology to remove the CO2 from the flue gas. And how many of the CCUS project number is? That is more than 1,000, because we can count. We have to remove a lot of amount of the CO2, so you have to have thousands of the million ton CCUS projects. Thank you.
All right, thank you. And the next question is from an anonymous attendee. In your view, is there any mature methods / ways available yet to safely capture CO2?
Sorry, you give me a new question. I just read the question on the talk. So is there anybody ask you a question?
Sorry, so is there any matured methods available to safely capture CO2?
Actually, I have to answer this question using these pictures. I have told to you, mature technology, I think from now on, today's, that is for this one, chemical absorption, that is the MEA, MDA, DA, capture the CO2 from the flow gas, that is mature. But the problem is the energy consumption. The problem is the capture cost, because the capture cost is too high. Maybe for other technologies, like the oxy-fuel, maybe they have more higher capture cost. So I think for today's choose for this one is the only choice for us to use in the power plant to capture CO2. But actually, if you capture the CO2 in the chemical plant, you can use other things like this one, low temperature distillation, and some of the other technologies. You can use it because when the CO2 concentration goes very high, maybe more than 60%, you can use this kind of technology. It will be much cheaper than other technologies. So for different concentrations of the CO2, you have to use the different of the capture technologies. That's my answer for your questions. Thank you.
Right, thanks. And just a comment, not a question, from Steve Tate. So he thinks that the development of high performance green inhibitors should take much more than the research for CCUS application.
That's right. I think your comments is correct, because we have to find more effective corrosion inhibitors, and at the same time, it is green inhibitors. It will have not much environmental effect underground, to the underground water, to the human being, to the some other things we need to be coming out or something like that. maybe it will also go into the oil and gas, coming to the chemical plant, to the refinery. It may have some of the impact on the gas line like that. So that is important. But I have to say that we have to consider about the impurity, the impact of the impurity on the inhibitor, and the effect of the inhibitors. Maybe what we use today, the inhibitor here is working very good, but the impurity, oxygen, NOx, SOx, H2S come inside together. I think together maybe doesn't work. Inhibitor doesn't work. Efficiency going down directly like that. So thank you.
Thank you.
And just one more question. What amine is the most commonly used?
Maybe I think in the gas purification industry, they use MEA and MDA. For nowadays, MDA may be more commonly used, as I know. Maybe in Sichuan province, they have a lot of gases have to purify, remove the CO2, remove the H2S. So MDA is the most used one. Thank you.
All right. Okay. That's all our questions for today, and we've come to the end of the session. Thank you, Professor Yong Xiang, for your very interesting presentation. And for the rest of you, we'll see you next week for the third of 5 webinars. Thank you all for attending, and bye for now.
Thank you, everyone.
Thanks.
You can send me an email.
Thank you very
I will
much.
give you the PPT if you are interested. Thank you. Okay.
Okay, sure. Thanks.
Here is my email. Okay. Thank you very much.
All right. Thanks.
Goodbye. See you.
Bye.
Thank you,
Thank you,
Professor.
Thank you.
Professor Xiang.
Thank you. Thank you very much.
Bye bye.
Bye bye.